This is a fully functional addition calculator that I made inside the VR video game, Yeeps Hide and Seek. It uses 7-segment displays with the double-dabble algorithm to show the numbers, and I made a video on each of these topics on my channel. But you don't need to watch those to understand what I'll be talking about today, although it will provide a little more background or context. Or, you could just skip to the end if you want. Today, I will be talking about probably the most important part, in my opinion, the easiest part of this entire design, the addition itself. Kind of an important part for an addition calculator. So right now, my calculator uses two 7-bit binary numbers as inputs for the addition. That just means that each number has 7 inputs or digits, and my calculator replicates this input in-game by having 7 buttons, each going to a toggle connected transmitter for each number. If you don't know how to read binary, I have an explanation in my previous video, but again, those are not necessary to know for this example. Now, we need to start with how to even add binary numbers in the first place. Let's start with what you already know. If I had these two numbers in base 10, 1,536 and 8,728, to add them we would start off with the ones digit, and add the 6 and 8 together, giving us 14. And because 14 is at least 10, we'd have to carry the 1 from the tens place to the second digit, and place the 4 in the ones place. So next, we would look at the tens digit, and add the 2, 3, and 1 that we carried over from the last number, giving us a 6. And because 6 is not 10 or greater, we can leave it at that. For our hundreds digit, we can again just add the two numbers, giving us 12. So we carry the 1, and finally we add the 8, 1, and the 1 we carried over from the last digit, giving us 10. The 0 is then put in the thousands place, and we carry the 1. But because there is nothing for the 1 to add to, we can just put it in our 10,000ths place. So 8,728 plus 1,536 is 10,264. The reason I'm going over this is because adding in binary is almost identical to base 10, except for two key differences. The biggest and most obvious of these differences are being that the binary numbers are only made up of 1s and 0s, so there are no other digits. The second difference, though, being that in base 10, you know how when you get to the number 10 when you're adding, you carry the 1? Well, it's just like that in binary, except whenever you add and get the number 2, you carry the 1 to the next digit. Here's an example. We can set up this binary addition in the same way we can for base 10. So I have two completely random 7-digit binary numbers here to be added. So, just like in base 10, we start with the ones digit. So we add the two ones together, and we get 2. But like I said, when you reach the number 2 in binary, you have to carry the 1 to the next digit. So the first digit will actually be 0, and we carry the 1 to the second digit. For the second digit, we have to add a 1 and a 0, and a 1 from a carry. So again, giving us 2, put a 0 in the second digit, and carry the 1. So for the third digit, we add the 3 ones, getting us a 3. So we take the 2 and carry the 1, and then there will be a 1 left in the third digit. For the fourth digit, we add the 2 ones again, giving us a 2. So we put a 0 in the fourth digit and carry the 1 to the fifth digit. In the fifth digit, we just have a carry and the 2 zeros. So when we add, we get a 1 with no carryover needed. For the sixth digit, we just have a 1 and a 0 with no carry. So when we add this, we get 1. And finally, when we add the last 2 ones, we get a 2. So we can put a 0 in the 7th digit, and just like in our base 10 example, when we have a carry in the last digits, we can just put it into the next digit, so the 8th. So finally, now that we have our answer, we can check by using the method of a reading binary from the 3-digit display video. And we would get first number as 103, the second as 77, and our final answer as 180. So if we were actually to add these numbers together, you would see that we have in fact added 2 binary numbers. So now we need to get this into Yeeps with the logic gates. And unlike my other videos, this section will not contain a bunch of equations and math. You can recreate this binary addition with logic gates pretty simply using a repeating pattern of just 5 logic gates, scaling depending on how many digits you have, of course. So, looking back at our addition, let's focus on the first digits of this number, and figure out all the combinations we can possibly have. If both of the first digits are 0, then the output will be 0. Makes sense. 0 plus 0 is 0. If one of the inputs, though, is 1, the output will be 1. 1 plus 0 is 1. But if they are both a 1, the output of our first digit will be 0, because 1 plus 1 is 2. But we would have to carry the 1 to the second digit. So this is the truth table for the inputs and outputs of the first digit. And if you know some of the logic gates, then you may recognize this as the exact truth table of an XOR or exclusive OR gate. So for the first output in Yeeps, you can just plug the first digits of the added numbers into an XOR gate, and that will be the output of our first digit. Then for the second digit, we will need to know if there will be a carry. So we can also plug the first 2 digits into an AND gate, and that will check for if both of them are 1 and give us a carry if they are. For the second digit, we now, with the carry, have 3 inputs that need to be added together. So we can wire the first 2 up the same way we did the first time, with 1 XOR for the output and 1 AND gate for the carry. But we now also need to count for the carry from the last 2 digits. And we can do this by having another XOR and AND gate to check for a second carry. We would plug in the carry from our first digits and the XOR from the second digits. Then, finally, the last XOR will be the output for the second digit, and then we can put an OR gate between the 2 AND gates left, and that will be used as our carry. This design is very scalable because all you have to do is repeat the process for the second digits, taking the carry from the previous digits, and the final carry will be the output for the last digit. So that scaling is exactly what I did here for my final adder. I just scaled up the adder from the first 2 digits for every digit I needed. So I wired it up to my displays and inputs for my last video, and after some debugging and troubleshooting, I was able to create this. Before I show the final design, I want to show all the iterations I went through to get to this design, because I actually went through 5 different 7-segment display designs before this final one. The first one I actually still have sitting in my sandbox. It is 13 by 11 by 10 blocks, and uses only receivers and transmitters to connect from the inputs to outputs. My second one I unfortunately deleted, but it didn't improve much from the original design. But after I learned a few tricks, I challenged myself to make it only with wiring, and this would be the one that you may recognize from my first video. After repeating the building 5 more times and some crucial redesigns, it now fits in a 4 by 10 by 9, saving 1,070 blocks of space from the original design, fitting seamlessly behind the display on the sides. Looking at the before and after, you can see that they are completely different, and I have to say that I am proud of its improvement, considering it's my first build, and it uses no receivers or transmitters. But finally, enough of me yapping, here it is in-game. So here is the final addition calculator in-game. As you can see, we can add smaller numbers, like 2 plus 2, or we can add even larger numbers as long as they're smaller than 127. So, here's 50 plus 90, and 50 plus 90 equal 140. And if you check that on the calculator, that is correct. So, my in-game calculator is correct. We can even go up to numbers in the hundreds digit, and get up to 118 plus 122 equals 240. But again, we can all the way up to 127 plus 127, which gives us 254. I would have recorded this section in-game, but because of how much wiring there was, it wouldn't sync properly between the 2 devices, my headset and my phone. So, unfortunately, I had to do it like this with a voiceover. Before I end the video, I'd like to mention that I want to make a 7-segment display tutorial and some actual applications that may be more realistic in a community world type setting. Because I will not lie, these displays with double level can lag your game with enough people. Trust me, I do know from experience. I will need some time to make some semi-proper blueprints for the displays, so don't expect that to be the next video. But, for my 23 subscribers, I do want to say that I'm sorry that this video took so long, because in editing I discovered a problem, so I had to restart the entire recording process. So, take this as a lesson to listen to your recordings as you record, not after. Until then though, I'd like to thank you for watching, and remind you to keep learning.